much. Yeah, I'm just since a week in Regensburg, so all the work I'm presenting is actually done in Prague, and at the time I was still in Cambridge, and I forget very quickly. And most of the people actually which did the work, the measurements, is Thomas Jander, a PhD student in Prague, and also João Godinho, also PhD student in Prague. Very nice, friendly and capable postdocs. And okay, so we heard a lot about all what is interesting on antiferromagnets, particularly very fast dynamics. But there's still a problem, as we also figured out in all these talks we heard about the switching, that the origin of the switching, or what is actually switched, is not really clear, right? So detection of antiferromagnetic states is a problem. And of course, electrically, one can detect macroscopic states. One can detect many spins via magnetotransport. This is at least what we believed. What we maybe still believe, for example, the anisotropic magnetoresistance enables us to distinguish orthogonal antiferromagnetic states. And if you look in the experiments, or look in copper manganese arsenide, you not only be able, in principle, to measure orthogonal states, but you can also, in principle, switch orthogonal states by applying currents in orthogonal directions due to the broken inversion symmetry of the copper manganese arsenide within the crystal, which generates this staggered effective field, which couples in very well to the antiferromagnetic order. But if you look to the experimental data, for example, here in Camille's measurements, you see that it's not so simple. You're not just switching between two saturated states, but there is a kind of memristor functionality, which may be very interesting for application, implemented in these measurements. And the origin might be that you're actually not switching saturated states, but what actually this copper manganese arsenide contains in many small domains which switch individually. And it depends how many pulses you already applied, how many small domains you might have switched. Now, to make such a beautiful picture, you require a huge equipment. Usually these measurements are done on synchrotrons, and it is used beam XMLD measurements, which enable you to make such pictures. And there are two problems. First of all, you need this big equipment that you have to ask for times. And also these measurements are very difficult to do. And even more difficult to combine them with electrical measurements. So then this copper manganese arsenide, to stay with the copper manganese arsenide, has another interesting feature. It has also not only an inversion asymmetry, a broken inversion symmetry, but also a broken time reversal symmetry, which enables you in principle electrically to detect antiferromagnetic spins, not by a simple measurement of the ground state, but actually by measuring the direction of the spins, but actually measuring the direction of the torques when exciting the system, and measuring it not in linear response, but measuring in higher response. So this can be done, for example, when you pulse now your copper manganese arsenide with pulses which are not orthogonal, but which are now going along the same axis, but changing polarity, and you see a higher harmonic signal in the electrical response, which actually gives information about the torque you apply when you bring the system slightly, when you perturb slightly your magnetic system. However, this looks like you would expect, especially it looks also like you would expect, because those states seem to be remnant. So you have a duration of about, well, you can measure for a day or longer, and the state remains. There seems to be no decay, which is very different from the switching by 90 degrees. However, if you look again with the XMLD measurements, with the beam measurements, you see it's again not so simple. These are not in uniaxial systems. You don't have a saturated state, but you have domains which are separated by domain walls where the magnetization rotates. So what is actually, what would be very nice to have is a very simple and cheap alternative tabletop experimental setup, which you can use also to identify magnetic domain structures. Maybe at similar resolution the beam is enabling you. And here is a very simple idea which shows it's possible actually to do. If you generate locally a temperature gradient, so it's not the response to electrical current, but actually a response to a thermal current, and you measure carefully, so it's actually a very small signal, but also globally, you don't have to measure at this local place where you actually excite this thermal gradient, but you can do it at contacts which are far away from this, so globally, an electrical response. And to generate a small heat gradient, this is very simple. You can just use a focused laser spot, and you get a gradient, a Gaussian-shaped heat gradient, if this laser spot gets absorbed in the media of about 1 to 2 micrometer. You can do it also better. You can use a near field, a SNOM microscope, a scattering SNOM, where you generate a near field, and the interaction of the near field with the conductive material underneath, the plasmonic excitation, generates you a heat gradient which has a Gaussian distribution as well, but of the order of 10 to 20 nanometer. So the resolution of this could be much, much larger. And more interestingly, you may not only just excite a thermal gradient, you may use a wavelength, because this system is not wavelength restricted, which is in a frequency range where you can also excite antiferromagnetic resonance. So this is something which could be used, for example, in the terahertz regime as well. However, what I show you today, it's a response to a thermal gradient only. And there are two thermal gradients which are relevant. So one thermal gradient is just it's directed, it's going perpendicular to the plane down to the substrate. And if you have a material which shows an anomalous Nernst effect, for example, a ferromagnetic material with the magnetization in the plane, you would be able to measure, depending on the magnetization orientation, transverse to this perpendicular heat gradient, you would measure a thermally generated electrical signal. And actually this, in antiferromagnetic systems, can be exploited, for example, in manganese-free tin or manganese-free germanium, iridium, very much as shown here. And there will be a talk by Helena, which shows actually the application of this, or exploitation of a perpendicular to plane heat gradient to actually map domain structure in manganese-free tin. But what about systems which don't show anomalous Hall effect or anomalous Nernst effect, like, for example, the collinear copper manganese arsenide? In this case, you still have a possibility thermally to detect, because you have also a heat gradient which is in the sample plane. However, this heat gradient is now rotational symmetric, so it's not directed, at least not if you're not coming to an interface or to a boundary of your pattern structure. And then you can make use of the anisotropic magnetothermal power to actually generate a thermoelectric signal. Well, what is it? The thermoelectric magnetic power is nothing than the Seebeck effect, if you want, which is a result of the asymmetry of the density of states around the Fermi level, which generates you, due to a thermal gradient, a charge current. And the proportional, the factor for this, the Seebeck coefficient, if it's a magnetic system and there's spin orbit coupling present, then there is an asymmetry. For example, if the orientation of the ordering parameter, in our case, the L vector, is parallel to the temperature gradient, or if it's perpendicular to the temperature gradient. This means if you have a temperature gradient along the electrical current you generate and you measure, you will be able to distinguish, in principle, by measuring the thermal response, if the L vector is parallel or perpendicular, or collinear or perpendicular. And if you have a thermal gradient which is perpendicular to the electric field you are detecting, then you'll be also able to measure a 90-degree rotation if you want, but the orientation has to be 45 degrees, so minus 45 degrees with respect to the thermal gradient. This is known as the planar anomalous Nernst effect, or the transverse anomalous Seebeck effect, if you want. So what happens in a system now, in a perfect system where you have just a simple domain wall and you have two magnetic domains, antiferromagnetic domains, which are 90-degree rotated? If you are within a domain, you will measure nothing, because, as I said, your thermal gradient is rotational and symmetric. It will average out. There is no effective component of a current you generate. However, if you go over a boundary, if you go to the other domain, since Seebeck coefficients are different, you will measure the difference. And so you will measure more or less a signal which corresponds to the size of your heat gradient. And also, of course, to the size of the magnetic variation. And now we have patterned, for example, 4 different bars in the same material close to each other. And we're measuring the thermoelectric response along one of the bars. You see quite a complex structure. And if you compare this complex structure of the thermoelectric response with the beam measurements of the same bar, you will see that there is some correspondence of the domain structure and of the thermoelectric response we're measuring. And now if these bars, since they are patterned along different crystallographic orientation, the domain structure in those bars is also not necessarily the same. There are many effects which play a role. There is maybe, Helena will talk about this, or maybe not talk about this, but there will definitely be a paper about this. There may be also strain effects which affect the magnetization distribution in these bars. So as you can see, the domain structure measured by beam is all different in these 4 bars, and you somehow have a very similar thermoelectric response also in those 4 different bars. One has to say that the measurements of the beam have been done a couple of weeks before the measurement of the thermoelectric response. So the one-to-one correspondence is maybe not given. Anyway, we have heard from the talk of Pete. He has shown us that in a certain range of pulse current density, one is able actually to switch magnetic domains, 90-degree rotated magnetic domains, forward and backwards by just reversing the current polarity, shown here in this beam measurements, and also reproduced by AMR measurements, by transverse AMR measurement in such a cross structure. If we do a similar experiment, we have a cross structure, and this cross structure enables us to measure a thermal response, a vertical and a horizontal thermal response. And we can send a current pulse, for example, in one of these bars, and we measure after that with our anisotropic magnetothermal power measurements the response of the 2 bars simultaneously. And you see quite a complex thermoelectric response. If we now apply the pulse in opposite direction, you see that only along the bar, only along the bar where the current was flowing, the thermoelectric response has changed quite drastically, whereas only in the overlap of the bars where the current is flowing and the bar where I'm measuring the transverse response, the signal has changed only in this part. So obviously, the variation of our thermoelectric response after the current pulse has been applied shows us that something happened to the magnetic domain structure. So one can do this actually quite often. One can also measure the magnetoresistance along this, and you see a quite reproducible measurement of the same structure after applying the same type of pulses. So obviously, those features are of magnetic origins. So if we go now to a structure which is a bit wider, where we see interesting features which show us those kind of arc structures. On the top side, if we measure the longitudinal response and the transverse response, we see these features on the corners. Again, if we apply a number of pulses in one direction, on the opposite direction, we see that we can switch between the arc being blue on the top to an arc which is red on the bottom. And intermediate states can be also generated where 2 arcs are visible. What those arcs could be. And it's reproducible. So you can do this many times and you will always see a very similar distribution. This is the experiment on the left-hand side. And of course, you can imagine if you have such a kind of cross structure and you send an electrical current through this cross structure, you generate a spin-orbit field, mainly there where the current density is highest. This means in the bar itself, the current density is high. Here, the current lines can broad out. It's weaker, and then it gets, again, concentrated. So assuming a domain structure where the antiferromagnetic domains are aligned along the spin-orbit field you generate is reasonable. And assuming also an arc structure is reasonable, because domain walls, if they're not pinned otherwise, they will build those kind of arcs when they move from a constriction into a wider area, simply by minimizing the energy. And this is a simulation if we assume indeed such a kind of magnetic structure and using reasonable values for the anisotropic Seebeck effect. The transverse and the longitudinal, we get actually very much such a shape. As I said, it's very reasonable to expect such a kind of arc shape. In ferromagnetic systems, this is very well known, just to minimize the energy, the domain wall energy, you get those kind of arc systems. Now, let's go to the uniaxial systems, where the analysis of the signal is maybe more simpler. In a uniaxial system, you have two possible orientations of the L vector in copper manganese arsenide, and only the domain wall is the region where the L vector is rotating. So now, because you see these very narrow domain walls, we now go to our high-resolution method, where we use the scattering norm to identify the domain structure. And we are scanning. Well, if you measure with a SNOM, you always get two results. You get a result of the AFM, which tells you something about the roughness of the surface. And as you can see here, this 2 micrometer wide stripe, which is patterned here, is very flat, and you cannot see any structural defects on the surface. However, if you look now for the thermovoltage, you see all these spaghettis here, which is quite a complex structure. And those kind of things are most probably domain walls. Because what you also see that at each of those spaghettis, the polarity changes from plus to minus. And this is exactly what you expect theoretically if you come with your heat gradient, which is rotational symmetrical, and go over such a domain wall. Now, are they really domain walls? So because if they are domain walls, you should be also able to move them with a current. Like it's, for example, shown with this with a charge current due to the effective spin-orbit field, like it is shown in the simulation here. Yeah, doesn't work anyway. And so if we, for example, look into a certain area and we apply a pulse, you see indeed the structure has changed. And if we send a pulse back, you see again the structure has changed again. And you can repeat this quite often, and you will see always very similar features. So it's reproducible. So indeed, we see domain wall displacements, and we see enlargement of certain domains and reduction of others, which is in accordance with Zeeman type of domain wall propagation, right, where you have a field-like torque. So to really figure out if the material we looked into is indeed a uniaxial material, I spoke in the beginning about the transverse anisotropic magnetothermal power. This means our easy axis, if you rotate it 45 degrees to a heat gradient which we generate, we should be able to measure a signal which depends on the orientation of those things. And indeed, if we rotate now our easy axis by 45 degrees, which we simply do by patterning a stripe 45 degrees rotated, we can then generate a heat gradient which is not anymore rotational symmetric, but asymmetrical, simply because we scan this heat gradient on the boundary of the stripe. And the upper one, for the same easy axis, we see a positive signal. And on the lower one, for the same direction, we will see a negative signal. So we will see at such a bar a blue or positive, negative kind of things, except at the area where the domain walls are, there it can be different. It can be 0 or it can be even opposite sign. And indeed, this is what we see if we scan such a rotated bar by 45 degrees. We see clearly it's mainly positive on one side or maybe negative on the other side. And if we look with our more coarse laser method, we see, and then scan the whole long bar, we see that this remains true over the large bar. Obviously, you lose the high resolution of your SNOM method. So what happens to the large pulses? So we had a lot of discussion during this meeting that if you apply small pulses, there seems to be the spin orbit field seems to be effective, and we can indeed move domain walls forward and backwards. But if you have very large pulses, you get a very large magnetoresponse, and not really sure if this is of magnetic origin. Yeah? So at very large pulses, you start to degrade your device. But the less strong pulses seem to generate large magnetoresistance or large resistance variations, which may be of magnetic origin, but they are not anymore stable. They're not constant. They seem to decay, stretched exponential. And here we do this experiment now with larger current pulses. The virgin state, again, we have quite a complex domain structure in our bar. Now we apply a pulse of larger amplitude, 1.3 to 10 to the 7 ampere per meter square. And then, as you can see, nothing anymore is left. Most of the structure is gone. So now you can say, okay, maybe we destroyed it magnetically. If you wait for a week, the system recovers. You get the magnetic structure back. So there is, obviously, you have shattered this system in many small domains, most probably, which then condensate back to larger domains and get probably pinned on defects in the structure. And this has been actually verified, again, by beam measurement. If you have a beam measurement from a structure where you have quite large magnetic domains, then you send a current pulse of very similar current density through it, you see that these large domains, at the place where the current density is high, so the current was sent along this direction of the cross, these large domains have scattered in small domains. Now you cannot wait for a week in the beam, but with your laser system you can do it. So most probably if you would have waited long enough, you could see also that those domains condensate back to larger domains. So to see that there's also a resistance variation when you have this spin-orbit torque polar switching, the same material now, you see by forward and backward sweeping, where you see this antiferromagnetic domains moving, there seems to be a regime where the resistance is switched and the resistance variation do not decay. So those things are like pinned. Also, these measurements, it takes of the order of 15 minutes. So during the 15 minutes, the magnetization distribution, or the magnetic distribution inside this area, which is about 500 times, I don't know, 200 nanometer or so. Oh no, 2 micrometer actually. 2 micrometer times maybe 500 nanometer has not varied much. But if you increase the current density slightly, then you come suddenly to such a regime where you get those stretched exponential decays, where you lose the large magnetic domains. So maybe to make the summary of my talk, what I have shown you is a kind of new type of scanning microscopy for antiferromagnetic system using the magneto-anisotropic Seebeck effect, where I have used 2 techniques. One is a wavelength wavelength restricted far field method and a high resolution near field technique. Then we have observed with this far field technique large domains which are affected by the patterning if we pattern stripes along certain orientations. And then I have shown you reversible and current polarity dependent spin-orbit torque switching and correlated resistance variation. And so both uniaxial but also biaxial systems. And I have, on the end, I've shown some examples that if you apply a large current, that you actually seem to shatter these big domains into small domains. Thank you for your attention.